Energy flow. We've defined that the amount of energy, change in energy, is found through the sum of heat and work. We look at the heat, thermal energy, gaining or losing from a system, where a system is what is being studied, and work done on the system or by the system, positive or negative. Another example to kind of understand the energy flow is you think of a ball, a billiard ball again, rolling across a table as a certain amount of initial kinetic energy, and it collides with the second ball at the end of the table. So we already kind of discussed this. You have this billiard ball that has its initial amount of kinetic energy of motion, that's how it's moving. And as it then eventually hits the second ball that's stationary. The first ball then loses all of its kinetic energy and itself remains still, constant at a point of collision. The total change in internal energy for the first ball is the difference then between the initial kinetic energy and the final kinetic energy, which is 0. The first ball lost all of its energy. Now, according to the first law of thermodynamics, it must have been transferred to the surroundings. Since the ball had an initial amount of kinetic energy, right, and then it was rolling around, just went down, 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 and has a certain amount of kinetic energy, and then it collides with this other ball that's here. So this is ball 1, and then this is 2, and then the second ball keeps moving, but the first stays still. So that kinetic energy is lost because it remains still. So it's 0. However, that energy just doesn't go nowhere. It has to have been transferred to the surroundings. The energy lost by the system must exactly equal the amount gained by the surroundings, the pool table and the second ball. So that energy, some of that energy was transferred to the second ball because the second ball started to move. If the second ball didn't move, it wouldn't have been transferred. Some obviously also was transferred to the pool table itself, but due to the collision, it transferred its energy to the second ball so the second ball can keep moving along. Now, sometimes there can be little bumps in the road where that can change a little bit. So if you think of just a smooth table, so if you're looking at this image right here, a smooth table, there's no cracks in the table, there's no static friction, there's nothing really going on to keep anything from rolling around smoothly. So as a billiard ball here rolls across a smooth table and reaches the other end, it collides with the second ball, just like you can see. The initial kinetic energy is 5 joules, where some energy is lost to the surroundings, some energy is lost to the pool table, and then the kinetic energy at collision is 4.5 joules. Most of the kinetic energy is transferred, as you can see right here, where the heat, Q, is negative 0.5 joules because heat was lost, right? So there is this ball that's rolling down the table. It lost some heat to keep going down. The system loses some thermal energy. Now, work was done by the system. That's why it's negative 4.5 joules, because it transfers its heat. So work was done by this ball. So then we say that the total energy is Q plus W, which is negative 5.0 joules. The kinetic energy after the collision is therefore 0 joules. Now, what if you have a table that has a little bit of bumps in the road? It's not as smooth. A billiard ball rolling down a rough table loses most of its kinetic energy through friction. Less than half of its initial kinetic energy is transferred to the second ball after collision. So if you look here, the initial kinetic energy of this ball is still 5 joules of energy. Now, because there's some bumps and some friction, it's not going as smoothly. there's more heat loss because it needs to continue to roll down. So 3 joules of energy of heat is lost. So the kinetic energy at collision, therefore, is 2 joules. So here, the work is negative 2 joules. That was the amount the system needed to collide. It lost 3 joules of energy. So your total energy is negative 5 joules. The kinetic energy after collision is 0 joules. Putting this into a little practice, thinking of transferring and what we're looking at specifically, heat or work, let's look at this example. Identify each energy exchange as a primarily heat or work and determine whether the sign of energy change is positive or negative for this system, and the system is defined. So let's look at the first one. Sweat evaporates from skin, cooling the skin. Sweat is the system. So in order to sweat absorbs energy as a form of heat from the surroundings. So heat here is the energy exchange. And the energy exchange, because in order to sweat, what's happening is the sweat is gaining heat from the surroundings. The change in energy is positive. A balloon expands against an external pressure. The contents of the balloon is the system. So the air inside the balloon works by expanding against the external pressure. So in order for a balloon to get larger, the contents of the balloon are working to expand its pressure on the inside of the balloon to make it larger. Therefore, we're looking at work here. And we're thinking, okay, well, work is being done by the system. In order to expand, the contents of the balloon have to work against the surface of the balloon. Therefore, since it's being done by the system, the change in energy is negative. Now, last one here. Aqueous chemical reaction. Mixture is warmed with an external flame. The mixture is the system. So if you have a mixture and you're adding there's a flame, you're adding heat. So we're looking at heat here because the thermal energy is changing since the temperature is changing. And heat is being supplied to the system, therefore it's positive, and your change in energy is positive as well. So it's important to understand if you have a temperature involvement, you're thinking thermal energy and heat. When you're thinking of pressure and expansion, you're thinking of work. And then you just see, all right, what is the system doing? Is it gaining or losing? Is it being done by the system or not? There you figure out whether your Q is positive or negative, which then tells you whether your change in energy is positive or negative, and the same goes for the work. So just as a little recap, sweat evaporates from skin, which cools your skin down. We're looking at sweat as a system. So in order to sweat, the sweat absorbs energy from heat. You're hot when you sweat. You're absorbing that heat from your surroundings. So immediately that means you're thinking of heat as your type of energy exchange. And since it's being absorbed to sweat, therefore it's positive. Now, a balloon expands against an external pressure. When you're thinking of blowing up a balloon, you're adding pressure because of the molecules inside the balloon. However, in order to get bigger, in order to go against that pressure, they have to do work. So you're looking at work, and it's negative because it's done by the system. An aqueous chemical reaction mixture is warmed with an external flame. If you're putting, just like in a lab, a beaker on top of a Bunsen burner, an aqueous chemical reaction, you're adding heat. Heat is supplied to the system. The reaction mixture, that whatever is in that beaker is the system, and you're adding heat by a flame. So you're looking at heat, and since you're supplying the amount of heat it's being absorbed, it's positive. The gas in a piston warms and absorbs 655 joules of heat. The expansion performs 344 joules of work on the surroundings. What is the change in internal energy for this system? So we're looking at internal energy. So internal energy is equal to, of the system, heat and work. Now immediately sometimes students think, all right, I have my heat and my work, I'm going to sum it up together and then I get my answer. However, you have to first define what the system is doing. Is it absorbing or losing heat? Is it doing work, or is work being done, so that you have the appropriate signs before you plug it into the equation. So looking at heat, a gas in the piston warms and absorbs 655 joules of heat. So that is positive. It's absorbing 655 joules. Then it says the expansion performs 344 joules of work on the surroundings. So work is being done on the surroundings. Work done by the system on the surroundings. Therefore, it's negative 344 joules because it's done on the surroundings by the system. So then you would plug in 655 joules plus negative 344 joules, which then gives you that your internal energy of the system is 311 joules.